And next talk is by William DeRocco from University of Santa Cruz about reconstructing the mass function of free-floating planet with Roman.
Okay. Yeah, just try to figure out how to. Let's see if I can get this on here. Should be. All right, can people hear me, or is this not great? It's okay. 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 Now people can hear me. Okay. Yeah, so my name is William DeRocco, and I'm going to be talking today about free-floating planets in the era of Roman. So before I dive into the meat of the talk, I just want to open up with a bit of motivation. I think that definitely all of you have now seen this plot at least once, if not multiple times during this workshop. And as Sam just showed, this is sort of the discovery space for Roman's microlensing survey, plotted on a plot of semi-major axis of the planet versus the planet mass. And so this is shown a lot, and this is a great plot. But one thing that I think is often overlooked when this plot is shown is the fact that the parameter space doesn't actually just cut off at 100 AU. Actually, it extends out well beyond this, all the way to infinity, which is the domain of sort of fully unbound objects. And so there's a reason that it's not usually shown, though. And that's because we don't really know what's out there, right? So in keeping with sort of the old notation that cartographers would use for the regions of the map that they have no idea what's going on there, this really constitutes some kind of terra incognita for planetary demographics right now. That being said, what's really exciting is that in the past few years, the really extensive efforts, the decades-long efforts of ground-based microlensing surveys like MOA, OGLE, and KMTNet have started to reveal the first hints of the population of what lives out there. And so what are these? Well, these are the free-floating planets. These are planets that are fully unbound from any star system. They're just drifting through the interstellar void. And what's very interesting is the fact that these initial observations that we have from the ground suggest that these planets might actually dramatically outnumber their bound counterparts in the Earth mass range, for example, by up to 20 to 1. So this isn't just some small fraction of planetary demographics. This could actually be the majority of planets in the galaxy. And yet it's something that is very often overlooked just due to the difficulty of observing these things. So this is all very exciting, but current observations right now really only provide a tantalizing hint of this population. But the reason I'm talking here today is because that's going to change with Roman. Roman is expected to observe hundreds, if not thousands, of these events. And so for the first time, we're really going to have the opportunity to leverage statistics to start understanding the origins and demographics of this free-floating population. And so there are two primary questions that drive my research right now. The first is what might be out there? So what should we predict? What should we expect to find when we look? And then the other one, which is a big one, is what can we actually see? What will Roman be able to do? And so I'm going to hopefully address both of these in the talk today. And so with that, I will dive into part one here. What might be out there? So to start estimating what might be out there in the FFP population, we have to talk a little bit about origin scenarios. The origins of FFPs are still an open question. There's very little known about them, but a lot of mechanisms have been proposed. And these range from star-like formation mechanisms, so the direct collapse of gas, for example, where these things would constitute basically very, very low mass failed brown dwarfs, all the way to planet-like formation mechanisms. So this is something that has been formed within a protoplanetary disk, like a planet, and then is subsequently ejected by gravitational scattering, which we just heard about, either by planet binary interactions, for example, or by planet-planet interactions. But the critical thing here is that all of these different processes actually imprint different features on the resulting distribution of free-floating planets. So direct collapse generally only works for very high mass planets, and it produces them with a very low relative velocity. Planet binary interactions are very violent. They can kick things out with a high relative velocity, and they operate on sort of intermediate mass planets. Planet-planet interactions are preferential for sort of the lowest mass end of these things, kick out with roughly an intermediate velocity. And so because of this, you can sort of imagine already plotting these different populations in these origin scenarios on axes like this of, say, mass versus ejection velocity, okay? And you'll see that each of these different processes is occupying a different region of this parameter space. So already this provides motivation that if you could reconstruct the mass function of free-floating planets, you'd start to immediately get insight into their origins and the formation processes that led to these things. Now, this is just a cartoon. So if we want to actually be able to do that, we need to rely on simulations. And so there is an extensive body of literature of dynamical simulations that study the production of free-floating planets. However, one of the challenges is that the majority of these simulations kind of start from preformed planets on set fixed orbits that are fairly arbitrary and possibly unphysical. And so because of that, it makes it very challenging to connect the results of these simulations to actual expectations for the galactic population of free-floating planets, right? So that is where the work of me and my collaborator, which actually the first results just appeared on the archive a few nights ago, that's where our simulations come in. So we're running dedicated simulations. We've run 2,000 so far of ab initio from just dust and gas disks, the formation of planets, their evolution, their migration, and their subsequent ejection by gravitational scattering. And we've also done this for a large set of different stellar architectures. So single star systems, wide binaries, close binaries. And by marginalizing over the results from these different populations, the hope is that we can start to make first estimates of what the actual galactic population of free-floating planets would be. And the really exciting thing about by starting at this ground level is that you can make a direct connection between predicted observable features in the free-floating planet mass function and the fundamental physical parameters and environments that induced these features in the mass function. So your first question might be, well, we do have existing observations. How well do these predictions match on? And the answer is actually surprisingly well. So if you look over at this plot here, the blue dots are the predictions from our simulations. The green and red band constitute 1 sigma uncertainties from a power law fit to existing observations from the ground of free-floating planets, which you're actually going to hear about right after this. And so what you'll see is that there's actually a very good correspondence between the two, which was very surprising to us, because I want to stress that our simulations were in no way tuned to existing free-floating planet observations. We just plotted them on top of each other and found this, which was really, really heartening, if also a little bit surprising. But so we predict a power law that's very similar to what's been already observed. However, you'll notice that what I'm showing you right here is only the sort of higher mass end, where we really have good data from the ground right now. When you move below about an Earth mass, that's really where we enter this terra incognita, because we don't have sufficient statistics right now to make particularly good estimates of what might be out there. And interestingly, this is exactly where our simulations differ quite wildly from just a naive power law extrapolation. We predict a significant dearth of Earth mass planets and then a much shallower power law down at these low masses, sort of Mars and below. And so what's really exciting about this for Roman is that this provides a testable prediction that we can go after with Roman and try to explore this low mass range that's going to tell us things immediately about the fundamental physics that is driving the formation of FFPs and the association to other planet formation theory as well. And so what's nice about these simulations is that I unfortunately really wish I did, but I don't have the time to go into all of these different features, but they can each be directly tied to fundamental physical things that are occurring. Wow, okay. So key takeaway here is that free-floating planets provide a unique window into planetary formation and system evolution. Now, this is all great, but you might be wondering, okay, but can we actually see this? What can we actually see? And there's a catch. The catch is that microlensing events don't give a direct mass measurement. We'd love to have the mass function, but we don't just get that for free. Rather, they give you sort of an event duration. And this is a degenerate combination of the mass of the lens, the distance of the lens, and the velocity. And so that makes it extremely challenging on an event by event level to pull out a mass, right? Unfortunately, that's sort of what we've been forced to do so far because we don't have that many events. So we have to kind of tackle it as best we can on an event by event level. But that is going to change with Roman because, as I said, we are expecting hundreds to thousands of these observations. So it's going to provide the first opportunity to really leverage population level statistics to reconstruct the free-floating planet mass function. And that is the basic premise of the work that I've been doing with collaborators at Lawrence Livermore, one of whom is in the audience, as well as Samson Johnson, where we are constructing a Bayesian inference framework by which you can use population level statistics to go directly from your population of TE, pi-e, rho parameters from your microlensing events into a reconstructed mass function. And so I want to stress that these are very preliminary results, but what you see here in black are injected mass functions. On the left, you see the power law extrapolation from existing data. On the right, you see this sort of prediction from simulation. And the blue error bands here are the 90% confidence interval that we get upon applying this Bayesian framework. And what you'll see is that, again, very preliminary, but it's pretty heartening initial results that Roman, in the full Roman survey, will be able to reconstruct these particular features and, for example, find this peak at super Earths if it exists. And that is going to be directly, you can directly tie that to the formation of these planets. So the key takeaway here is just that by leveraging population level statistics, Roman will be able to start answering fundamental questions about the demographics of free-floating worlds and the associated questions that come with planetary formation. And so I'm going to summarize just by reminding you of the two things we talked about in terms of what might be out there. Free-floating planets really provide a unique window into planetary formation that has sort of been overlooked because we haven't really been able to do this yet. And then in terms of what we can see, Roman will be able to go after this mass function. It'll be challenging, but we can do it. And we're going to start being able to do really, really interesting science with the results. And so with that, I just want to talk a little bit about what's next. There's still a lot to be done. On the theory side, I'm working on running a lot more simulations over a lot of different stellar architectures, incorporating different origin scenarios as well. So more of these star-like origin scenarios, as well as stellar flybys from the galactic environment. And I also just want to get the rest of the theory community involved. I think now is the time to start thinking about these things. On the observation side, we're continuing to build out this Bayesian inference framework. I want to extend it to velocities as well, because I've shown you that the mass versus velocity space is a particularly good one. There's the problem of false positives, which is a big elephant in the room that we're going to need to address if we're going to be able to do any of this successfully. And so what I want to conclude by is just saying that currently I'm serving as the co-chair of the Free Floating Planet Working Group for Roman. And so we're actively recruiting right now anybody on the theory or observation side who wants to get involved in these efforts. And so, yeah, if you are willing, free-floating planets present a really exciting opportunity. I really believe they do, but they're going to be a huge challenge. And so if you are willing to sort of strap on your boots and venture forth into this unexplored domain with us, please shoot me an email because I'd be happy to get you involved. And with that, I'll conclude.
Thank you, Will. We have time for one quick question up there.
Hi, so in your simulations, you mentioned that you had different galactic populations built into it. And so I was just curious if if you expect the mass distribution to change with things like metallicity and stellar age distributions, bulge, thin disk, etc.
Yeah, so that's a great question, and it's one of the reasons that we're running a lot more simulations is because the galaxy is actually quite diverse, and so you want to incorporate as much as you can. So this is sort of an ever iterative process of improving. I think that in terms of sort of protoplanetary disk parameters and stuff, one of the big ones that we see that can affect the results is actually the disk viscosity. I'm sure metallicity might also play a role as well, but the disk viscosity is one where that will actually shift the location of that peak that I showed you. And so these were primarily low viscosity simulations because that matches well with bound radial velocity measurements. But you know, there's uncertainty there. It's an open question, and that's the sort of thing that could start to smear this thing out.
So there's one question from Eve Lee online. Is there a simple way to understand what's so special about Earth mass, that causes the death, and how robust is it against assumptions in your calculations?
Yeah. So that feature is actually really interesting. So that transition between that sort of valley and then peak structure has to do with when migration becomes efficient. So below an Earth mass, you're dominated in the galaxy by planet-planet scatterings, and these are usually occurring at fairly large semi-major axes. Once you get down, and so obviously that falls off as the mass gets higher and higher because it's harder and harder to eject things. Once you transition at about an Earth mass, migration in binary systems becomes efficient. You're reaching a sort of a pebble isolation mass where you can start to migrate inwards towards the inner binary very rapidly. And as soon as you migrate in there, scattering off the inner binary is extremely effective. So that peak structure comes from the transition into dominance by binary ejections. I hope that helps.
Thank you. I think we're going to move to the next talk. Thank you.